Hi, hello. I'm here with a new video about intelligent scanning using deep learning for MRI, and this is not actually a scientific article posted by not a scientific article posted in TensorFlow blog, and let's read it. And by the way, it's my first time to read this article too. Here we describe our experience using TensorFlow to train a neural network to identify specific anatomy during a brain magnetic resonance imaging exam to help improve speed and consistency. So MRI is a 3D imaging technique that allows clinicians to visualize structures in the body non-invasively and without ionizing radiation, and it is widely used and powerful, and due to its superior contrast between soft tissues such as gray matter, white matter, and it is quite unique ability to not only visualize anatomy but also depict physiology and function like blood flow, perfusion, and diffusion. So one of the key strengths of MRI is being able to image specific locations in the body at an orientation best suited for the purpose of the exam. So it means the operator must plan these scans carefully to yield the best possible images uniquely oriented for each patient to visualize the specific structures. Here you see that example of a localizer acquisition. As part of the MRI exam, the scan operator first acquires a set of low-resolution localizer images. So, like figure 2, from which approximate location and orientation of undesired landmarks can be identified. So these anatomical references are then used to manually plan the exact locations, orientation, and required coverage for images that will be used for the high-resolution scans that are used for diagnosis. This procedure is complicated as the orientation, location, and coverage needs to be correct in all three spatial dimensions. And the quality and consistency of positioning and orientation of the slices relies heavily on the skill and experience of the scan operator. This process can be time-consuming, so maybe it means machine is important that you use, can be time-consuming and difficult for complex anatomies. So that it makes it difficult for the expert to understand, especially when a patient is being scanned as a follow-up to previous MRI exam and they're trying to identify subtle changes in anatomy or disease progression over time. In the worst case, the correct images are not obtained and the patient must return for another procedure. So they define the solution here. So they find a solution as deep learning based framework for intelligent MRI slice placement for several commonly used brain landmarks. Our approach determines planar orientations automatically using the standard clinical localizer images. This allows the scan operator to consistently get patient-specific slice orientations for multiple anatomical brain landmarks, like those mentioned parts. So we utilize the TensorFlow library with the Keras interface to implement the DL-based framework. We choose TensorFlow since it provided ready for support for 2D and 3D CNN, which is the primary requirement for medical image volume processing. Unlike prior approaches automate slice placement, our framework uses deep learning to determine the necessary planes without the need for explicit delineation of landmark structures or customization of the localizer images. It can also warn the user in the case the localizer images do not have enough information for automatically determining best scanned planes. So what else they say? Another key advantage of our generalized DL-based approach is that it can be easily extended across other anatomies. Using the exact same architecture but new training data, we can develop automated techniques for new anatomies. So something like this. Data appropriate for further processing, user feedback, location and coverage, and orientation. So this is the 3 steps of the method. In the first step, we check if the given localizer image is suitable to identify the plane for the desired anatomy. This is achieved by using file layer. And we use the built-in TensorFlow functions for image manipulation to achieve data augmentation during the training of localizer and identification of anatomic coverage, and we locate the spatial extent of the desired anatomy of the steps. The next processing steps to be robust to changes in imaging parameter settings across hospitals. Okay. Then later they identify the precise plane, orientation, and location. So the entire process takes 3.5 seconds on a high-performance CPU. So came from more than 1,300 subjects and were acquired using various scanner models as General Electric, I guess, and field strength from several clinical sites across the globe. So this is the method to benefits of dimension, the benefits of TensorFlow, and that's all, I guess. So I think this they mentioned the product and some advertisement, I guess. Anyway, I find this article quite interesting, and thanks for watching this video. I wish you find this useful and have a beautiful day. Bye bye.